All right, so we are going to continue talking about light. Uh, Last unit we looked at Snell's law. We talked about reflection and refraction. We're going to continue talking about reflection and refraction, but this time we're concentrating on how light reflects off of different types of mirrors and how light refracts through different lenses. So we'll start out talking about mirrors. The first type of mirror we're talking about is the one that you're most accustomed to, which is a plane mirror. And we're not talking about plane as in ordinary, we're talking about plane as in flat, existing in one plane, so to speak. So a plane mirror is a flat, smooth surface that reflects light regularly. Any object placed in front of that mirror is a source of diverging light rays, light rays that are spreading apart. Any image seen in a plane mirror will appear to be the same distance behind the mirror that the object is in front of the mirror. And the image will be equal in size, unfortunately for some of us. It will be upright. It will be reversed from left to right, which is important, for Scooby-Doo, because, when he's running from the monsters and then, he comes out from around the corner and the monster's there and he acts like he's the monster's reflection in the mirror. So when the monster raises his left hand, Scooby needs to know that he has to raise his right hand. You guys get the idea. Anyway, so the image seen in a plane mirror is going to be the same size as the object. It's going to be upright, and it's going to be reversed from left to right. And it's going to appear to be the same distance behind the mirror that the object is in front of it, even though light can't exist behind that mirror. So we'll talk real quickly about how a plane mirror works. So if this is our mirror, and here's our person standing out in front of the mirror, happy because, he's thin. Light going from the top of this person's head to the mirror follows the law of reflection, bounces off at the same angle, and the person sees the light. Same thing for light coming from down here near the person's foot. It's going to travel to the mirror, follow the angle of reflection, or the law of reflection, bounce off the mirror at the same angle, and enter the person's eyes. So, we'll use a slightly different color to show you the reflection part. The person sees those light rays as coming in a straight line. So if we follow the reflected ray from the top back through the back side of the mirror, and the reflected ray from the foot back through the back side of the mirror, we end up with an image. The person sees the foot down there. And of course there's light rays coming from everything. We're not going to draw everything, but... And obviously I didn't measure anything, so this isn't perfect, but the distance that the image is the same distance that the object is. And everything looks to be the same size because it's all going in straight lines and everything. Okay, so that's how reflection from a plane mirror works. Another type of mirror we're going to talk about is a concave mirror, which is a curved mirror. It curves inward like a cave. It reflects light off of its inner surface. This could be considered part of a sphere with a radius of r. The point at the center of the sphere, at the length of r, is called the center of curvature, or C. And then we draw a line from the center of curvature to the mirror, which is called the principal axis. Because a concave mirror is curved, each point on the mirror has a different normal. So when light rays strike different points on the mirror, they will still follow the law of reflection, but because each point has a different normal, they will reflect at different angles. And so rays of light parallel to the principal axis will reflect at an angle and cross the principal axis through what's called the focal point. So curved mirror like this can be used to focus light from distant objects to basically a single point at the focal point, which is why they're used in things like telescopes, reflecting telescopes. The distance from the mirror's surface to that focal point is called the focal length, and this should be exactly 1/2 of the distance to the center of curvature. Or another way to put this then is that the focal length is 1/2 of the radius. Okay. Back to that. So basically, if we take a sphere, that's pretty good. Right in the middle would be the center of curvature. This would be R. If we then take away some of that sphere and the inner surface is reflective, we now have a concave mirror. So this would be the center of curvature. The distance from the center of curvature to the surface of the mirror would be the radius. And halfway from the center of curvature to the mirror would be the focal point. And the distance from the focal point to the center or to the surface of the mirror is the focal length, which is a small f. Okay. Now that I've shown those to you, I'm going to get rid of the radius and the focal length, and we're going to talk about how light reflects. We have a distant object, a light ray parallel to the surface of the mirror will reflect at an angle that causes it to pass through the focal point. Okay, I'm actually going to get rid of this object. If we have a distant object like a star, something way out there in the universe, all of the rays are going to end up being parallel to the principal axis. Which is this thing right here, this line we've drawn to the surface of the mirror. All of the light rays will be parallel to that, and they'll all reflect back through the focal point. And so we get an image of whatever thing we're looking at show up right there at the focal point. That would be called a real image because light can pass through it. For mirrors, real images are formed in front of the mirror, on the same side of the mirror as the object. Any image that appears to be behind the surface of the mirror, like the image of yourself in a plane mirror, is called a virtual image because that seems to exist where light rays can't actually pass through. Okay? Real images, another cool thing about real images is that they can be projected onto a screen. We'll take a look at a real image in class. Talk real quickly about ray diagrams. A ray diagram is an easy way to kind of get a general idea about where a image would show up with these different types of mirrors. The first ray starts at the top of the object it is drawn parallel to the principal axis, and so then it reflects back through the focal point. Ray number 2 would start at the top of the object and is drawn straight through the center of curvature. Because of that angle, when it hits the mirror on the other side of the center of curvature, it reflects straight back through the center of curvature. So basically, we just have a straight line. Ray number 3 starts at the top of the object and is drawn through the focal point on the front side, and then it reflects back parallel to the principal axis. So, I'll show you those real quickly. For a concave mirror, there's our mirror, here's our principal axis, this is the center of curvature, and this is the focal point. If we put the object out here somewhere, ray 1 is parallel to the principal axis and reflects back through the focal point. Ray 2 goes straight through the center of curvature and reflects back straight through the center of curvature. And then ray 3 goes through the focal point and then reflects back parallel to the surface. 2. Oops. And this one is 3. And right here where the 3 rays cross is where our image shows up. Okay? So this image, compared to the object, is reduced in size. It's smaller than the object is. It is inverted because it's upside down. And because it's on the front side of the mirror, the same side that the object is on, it is a real image. So it's real, inverted, and reduced in size. That was an object that was beyond the center of curvature, and as you saw, the image showed up between the center of curvature and the focal point. It's real, inverted, and reduced in size. As you move the object closer to the mirror, the image gets farther away and it gets larger. When the object is between the center of curvature and the image, or in the focal point, when the object's at the center of curvature, then the image is also going to be at the center of curvature. It's still real, it's still inverted, and now it's the same size as the object. As you move it closer, put it in between the center of curvature and the focal point, then the image moves farther away and gets bigger. It's still real, it's still inverted, but now it's bigger, it's enlarged. So it's larger than the actual object. At the focal point, there's no image formed. And then if we move the object in between the focal point and the mirror's surface, then we end up with a virtual image that is upright and enlarged. Show you real quickly how that works. So here's our mirror, principal axis, center of curvature, focal point. We put the object in here. Then ray 1 still goes parallel and then back through the focal point. Ray 2, I forget what colors I used, so I'm going to just try to guess. Ray 2 is still supposed to go through the center of curvature. Well, that's behind the object, so it has to go that way. And then ray 3 goes through the focal point first, and then reflects parallel. Well, these aren't going to cross on the front side of the mirror, but if we follow their reflections back through the back side of the mirror, cheat a little bit, but they've crossed back there. And so that's where our object shows up, or excuse me, our image. And as you can see, it's behind the mirror, so it's virtual. It is enlarged because it's bigger than the object, and it's upright. A convex mirror is another curved mirror, but this time it curves outward and it reflects light off its outer surface. So for a convex mirror, the focal point and the center of curvature are behind the mirror, and that makes them negative. So the focal length always has a negative value. With these types of mirrors, the images that are produced are always virtual, upright, and reduced in size. I'll show you real quickly how those work. So this time it curves the other way. Center of curvature is back here. Focal point's back here. Object's out here in front of the mirror. Ray 1 is still going to go this way and reflect as if it's going through the focal point back here. Close enough. Ray 2 is still going to go as if it's going to pass through the center of curvature on the other side. Again, close enough. And ray 3 is going to travel as if it's going to go through the focal point, and it reflects back parallel. We follow this back through here. The three rays meet right here, and that's where our image is, the reflected rays. Okay? So our image is reduced in size, but it is upright, and it's behind the surface of the mirror, so it is virtual. Okay. This talks about the equation for the finding the actual where the actual image shows up using numbers, and how to find the magnification. We'll talk about the rest of this stuff in class and do some example problems. All right, we'll see you in class.